Ow. Exam 1, Exam 2, Exam 3. This is not a trend I like. The thing I noticed the most in all of this was the biggest difficulty occurred when I asked, what are the hypotheses? And then, okay, test your hypothesis. But if you don't know how to write the hypothesis, then how do you test it? And most of you can do the calculations when you had the information, but what did you draw from that conclusion? What was your answer? So I had hoped that this would be easier because more of it was, what's the hypothesis for this setup? This goes back to every question I've asked in class in these chapters. What is my hypothesis for the sections in 9 and 10? That was the thing I did, all of the ANOVA stuff we were just talking about. What are your hypotheses? That's where we start. So, review this. You will see this crap again because the final is comprehensive. You do get another sheet of information for the final. Just like you've had these formula sheets that you've been able to write up, you get another one for the final. And you can use the old ones. So, start now. However, I went back and I looked at the last times I taught this course. This average is not that far off from the average the last 2 times I taught this course. The exam 3 is the hardest. There's no doubt about it. So yes, it is incumbent upon me to create some better review for the final. I will work on that. It is on my goal for the rest of this week to have it to you Wednesday, ideally at the latest. I just have to write something up. I'm working on it. I promise I'll get something in. If you have questions, the key was posted today as well. Go look at that. Let me know what your questions are. Everybody in this room is capable of passing this course. No one is failing at this point. You are all capable of scoring a passing grade. Whether you like that passing grade or not is a whole separate ball of wax, but everybody can pass. Onward we go. When we do ANOVA, we have categories, and we are looking for variation within a category. Does which category we are in cause us to vary our response variable? Speaking of ANOVA, in the homework questions for chapter 11, it says do parts A through F, right? Back at the beginning of the exercises, down here it says use whatever statistics package you want, but here are all of the parts to all of the problems. So they're not rewritten in every part. You'll notice there are some other things up here at the top of the next page, parts G and F, that we don't do because I didn't cover that material. That's important. I want you to do the stuff we did cover and answer these questions for each of those pieces. Yes, ma'am.
So the A, B, C parts that it says only is everything before that? Not just the 46, but all of the questions before that, it's only those parts?
I believe that's what I wrote. Let me double check. Where's my copy of the paper?
Yeah, there's commas between them, so I read that only 46 did A, C, D, E, F only, or E, F only.
I got to get the piece of paper off the page. Hang on. Let's see what I actually wrote. Click, click. Signed homework. Poof. See the brace before that? 30, 34, 42, 40. All 5 of these should be done that way. That's why there's that extra brace around all of that. So for all 5 of those problems, do all those parts. A, C, D, E, F. 52 has its own parts. Okay. Drop that. So I was looking at which category I'm in for an ANOVA, whether I'm looking at one or two or more categories, I then want to be able to say, when these things change, something in our response variable changes. We have an effect or we don't. When I have an effect, I want to be able to quantify that, but that doesn't work with categorical data. It only works with numerical data, with quantitative data. So let's suppose I have bivariate quantitative data. All right, hang on a second. What? What's that mean? Bivariate, what's that mean? Two variables. Quantitative means they're both numerical rather than one of them being qualitative, categorical, nominal. So I've got number versus number. Ideally, this should be ratio data. Because that way there's a clear zero. And there's a clear meaning for that zero. There's the possibility that we can overlay this with interval data, but we can't do it with ordinal. We can't do it with nominal. We have to have more number ability. We did this back in chapter 3. I said, tell me what information you get when I give you numbers. 12.3 here. Given the number of windows open at the DMV, how long do I wait? Now, they've given me the wait time in seconds, so 385 isn't outrageously long. That's what? Almost 7 minutes. It's not a huge amount. But what happens? Is there a trend here? What do you think should happen as I open more windows at the DMV? I would hope wait times would go down. There should be a response, my y variable, just like we called it in ANOVA, to my independent variable, my factor, number of windows open. So how did we look at that back in chapter 3? Chapter 3 was all about visual displays of data and the way we interpreted the things we were looking at when we looked at our displays of data. What display did we use for this sort of bivariate data? What was the graph we were looking at? A scatter plot. This is exactly that data. Number of windows open across the horizontal axis and wait time in seconds across the vertical axis. And I can do this with a preliminary indication. You can now see, are we right? As more windows open, does wait time appear to go down? Or am I blowing smoke up your ass?
There's a tendency that it goes down.
There's a trend. It's not smooth. It's not a straight line behavior, but there's a trend here. So I know, yes, there is a pattern. It appears to be kind of a line-ish, but there are some clear distortions from a straight line behavior, and it seems to be going down. As number of windows gets bigger, wait times are going down. We gave that a name back in chapter 3. We said this type of relationship was weak and negative. Weak because it's not a tight cluster around the line, and negative because as one goes up, the other goes down. If they were going in the same direction, then I'd have a positive. Great. I could do a giant calculation. We even showed how to do it before, but I'll go through it a little more carefully this time, and I can get something we called a correlation coefficient. I've seen this before as well. It was again back in chapter 4 that gave me how closely these were related. And I'm literally looking for how close is this to a straight line. And we came up with a number that was always between -1 and 1 when we did this. And when it was negative, we were having that downward trend as one got bigger, the other got smaller. And when it was positive, we had an upward trend as one got bigger, the other got bigger. The command in Excel was done like that, correlation. I can actually figure this out directly. Yes, ma'am.
So sorry.
Oh.
This is the degree at what?
The degree of linearity. How straight a line that is, the degree of linearity. If I actually work this out by hand, please don't copy this formula down. It's not worth your time. The top here multiplies the difference from the average in the x times the difference. This is variation, isn't it? And this is the variation in the x's, then squared and square rooted. I've seen that before. What's that? I know that number. Except it's, yeah, squared is variance, square root is, yes. Okay, standard deviation, and then some product to get away from it. So it's measuring how they interrelate with each other. Gee, this sounds like the ANOVA, right? That interaction effect is on top, and then each one themselves has their standard deviation on the bottom. We usually give this the letter R. Same thing up here. And it's always between -1 and 1. By the way, it turns out this has a really nice relationship in terms of an angle. Technically, this is a cosine. It's a cosine of the angle between the two sets of data measured like they were vectors. If you never ever think of that again, that's perfectly fine. But the fact that it's a cosine is why I know it's between -1 and 1, because trig functions do that, right? They wiggle back and forth, and their highest spot is 1, and the lowest spot is -1. That helps me remember that part. So I say to myself, hey, if I get a number close to 1, I think this should be a relationship. If I get a number close to -1, I think this should be a relationship. There's no relationship means that R value should be 0. There could be another kind of relation. It might not be a straight line. It might be a curve of some type. It might be an exponential equation. But if there's R being 0 means there's no straight line relationship. It turns out we can actually do a test. We can have a hypothesis that says, I think the relationship is 0. And then I can test it with a t-test. Hey, wait a minute. I did something different. Why is df n minus 2? Wasn't df always n minus 1? Why is it n minus 2 this time? Say again? I got an x bar and a y bar, and I used them both. I need to subtract 1 from each of them. Great. And we do a two-tail t-test. That's why I'm using this set of null hypotheses. Now I can compute a critical value for R. That's an unpleasant idea. I think it's easier to do a p-value. Once I know this t calculated, let's look it up on the t-test. Now I'm giving you an Excel command for doing this because I'm never, ever going to do this test by hand. But let's see. Let's see some things here. I want to see how this works for our example. So I'm going to go get this spreadsheet off of our in-class example setup. Question 3 with the DMV data is on our Canvas page. Here is our DMV data. That gives me this scatter plot that we saw earlier. Again, let's scatter plot it. Insert. Well, there's a bunch of graphs right there in the upper corner. I'm going to insert a scatter. Click. If I hover over it, it'll actually say scatter or XY. Click that, and I get this option right here. Boop. That's the same picture we saw. Yes? I could go through and do all the calculations. I can do it right here, equals CORREL. There it is, correlation. It starts to fill that in automatically. I hit enter, or sorry, I hit parentheses because it wants me to give them the data. The X data is here, array 1, comma, array 2. Boop. Negative 0.0733. Okay. Great. A negative correlation, negative number. I'm happy to see this. I want to know a critical t-value. I could do that by looking up the t calculated, right? Or I could do a p on this. But I need the t-value if I'm going to do the p. So let's do the t calculated. I need to go back to the formula sheet again because I wrote it down. Here's my t calculation. I have the r. So let's put this back in place. T calculated. So it is r times, that's our r right there, equals r times the square root, SQRT, square root of what? The number of things minus 2. How many things are there here? Well, it says right up there are 5 of them. So 3 over 1 minus r squared, but that's in parentheses. So parentheses 1 minus r value, click, to the second. So here's my t value. Do you all still have a t table? Open up your back of the book. I think I have some t tables sitting here too. Yes. Here's a t table. Right here. Degrees of freedom is 3. I'm doing a two-tail test at 5%, 0.05. That's our normal, typically accepted level of significance. What is our critical t-value? That 5% that you are looking at says significance level for a one-tail test. Go up one line and it says for a two-tail test, you should be one column further to the right.
It's a 3.182.
See the difference? And we did say we were doing a two-tail. So-
It doesn't say it like that. I have the downloaded version from the files.
That's why I use the print one here, but I'll get the downloaded. I'll get the downloaded version to match. This should be on our Canvas page. But there, 3.182. Wait a minute. If that number is 3.182, and this number is negative 1.86, do I reject my null hypothesis or not? Well, what is my null hypothesis?
If the weight or the amount of registers increases, that the wait time will go down.
Is that my null hypothesis or my alternate hypothesis?
That's your alternate hypothesis.
The null hypothesis is that there's no relationship between these things. R is 0. There should be no relationship between the number of windows and the wait time. This is like Zootopia with the sloth at the DMV, right? Okay, people. Yeah, it doesn't matter how many windows are open. There's no telling what the time is going to be. But 1.865 versus 3.182, reject or not? Right, it's in the middle. And our rejection regions are out in the edges when we're doing a two-tail test. So no, we do not reject. Now I could actually look up a p-value here by saying what I want you to do is tell me the probability for this p-value. So equals t dot distribution dot two-tail, parentheses, put in that number. Oop, I've entered too few arguments. Right, because I forgot to put in the degrees of freedom, which is 3. Two-tail requires me to use the positive version. I forgot. So let's actually type in the number instead of using H4. We'll say 1.865. There we go. Should I reject or not? What was my tail? My alpha significance here. And this p-value is bigger than that. I reject when p is smaller than alpha. I don't reject. There is a relationship. I can now conclude successfully. There is a relationship here. Now, I actually did the calculations manually because I'm an idiot. To show you we can do it, you don't have to. And there's our tested value. And it does say down here that the t-distribution two-tail won't look up negative numbers. I had forgotten that until I typed it in. That's why it reminds me, but I did put it in here. So I can actually do a test to say, is there one or isn't there one? And regardless of the size of our data set, the process is the same. Here are 17% returns on mutual funds last year versus this year. Is there a correlation, a relationship between how your mutual fund did last year versus how they do this year? It would be nice if I could look at this data, and if I create the same sort of scatter plot, I can see this. Notice the horizontal axis is last year's return on investment, and the vertical axis is this year's return on investment. Is there a relationship between how you did last year and how you do this year? It does look like most of the data goes up as we go from left to right, but it is fairly spread out there. So I would agree with you, weak and if I go and I actually compute an R value here, I would expect an R value that is positive, but I wouldn't expect it to be all that close to 1. Might be a little lower down. And this is why I don't do this stuff by hand, because this is going to take forever to do by hand, and it's going to take me 4 button pushes in Excel. So I can now ask the question, if there is a positive relationship between last year's performance and this year's performance, what is it? If there is a relationship between how many windows are open and how long the wait time is, what is that relationship? The idea of regression or line of best fit is to quantify this relationship. So I'd like you to be able to tell me how much time will I save if I open another window? If the performance of the fund last year was 1% more, how much better should it be this year? I want to be able to put some numbers to this. I can then answer some predictive questions. Can I say, oh, well, when this goes up, this is how much more money you'll make? Or, hey, I open another register at the front of the store, the lines get this much shorter. I didn't go shopping on Friday. I stayed away from that place. But I'm pretty sure they were working with all hands on deck, right? How much faster did things get? So we're looking at linear relationships. That means we've got a straight line going on. I can do all sorts of other relationships, but they all basically come down to manipulating this one. And we'll save that for other classes. We do a lot of larger relationships and nonlinear regression behavior in decision analytics next semester. Now, when we think of straight lines, we think of an independent variable and a dependent variable. I can change x, and some changes will happen to y. But when I think of this in terms of, like our ANOVA, we had response and we had treatments and predictors. So I'm going to use that same terminology. My dependent variable is my response variable, and my predictor, my independent variable, is the thing I can make some decisions about, usually. My goal is to say, oh, when I make some changes here, I can then use that to predict what's going to happen over here. Each time I have a setting for my problem. We were talking about wait times at the DMV. If I add another clerk, my wait time should go down by this much. I need to know what this much is. That's my slope there. But it depends on our situation. Here are a couple of randomly pulled examples from the textbook. Sales equals 268 plus 7.37 times ads. For every additional units, here are millions of dollars. For every additional $1 million spent on advertising, sales should go up by $7.37 million. If I didn't spend any money on advertising at all, I'd still expect sales of $268 million. So this is the B, which in our graph is a y-intercept. That's what happens when our x value is 0. And this is our slope. For each additional unit spent, an increase of 7.37. Here, I'm running an insurance plan, and drug costs is 410 plus 550 times number of dependents. If you have no dependents, I should expect your annual drug cost to be $410. And for each additional dependent on your plan, whether that's a spouse, a child, whatever, I expect to spend another $550 per person on your drugs. So if you are getting insurance for you alone through my prescription drug benefits, costs you $410. Every additional person you add, this is how much more I'm going to spend. Roughly. Now, is this a perfect model? Only if our data was a perfect straight line. And you saw none of our data looked like perfect straight lines, right? So this is a rough estimate. Here's one with a negative slope. Miles per gallon is 49.22 minus 0.079 times horsepower. The more powerful your engine is, the less efficient it is. Big, powerful engines waste more fuel or use more fuel. And thus, for every time I increase horsepower, I'm going to go down in miles per gallon. But does it make sense to talk about an engine with 0 horsepower? If you have 0 horsepower, you're a brick. You're not going anywhere, are you? So this 49.22 as an idea on a graph makes sense, but in the situation of the problem, it isn't particularly useful. Same thing with this idea about rent versus square feet. The rent of your apartment is 150 plus $1.05 per square foot. Can you have an apartment with 0 square feet in it? I'm outside. That's not an apartment. There's no square footage here. I can't put my stuff in any. No, I'm going to just get rained on. So while it may have a value of 150, that's not meaningful in the situation of the problem. So these sorts of relationships describe a situation. But what they do not give me is cause and effect. Problem number 9 here. Car theft equals 1667 minus 35.3 median age. Car theft is the number of car thefts per 100,000 people by state. Median age is the median age of the population in that state. So the slope is negative 35.3. What does that mean in terms of this setting? That's a slope. Measures change in response for each change in predictor. So if median age goes up a year, what should happen to the number of car thefts? Goes down by roughly 35 per year older that the population gets. Old people have crappy cars, nobody wants to steal them, I guess. But that's just the interpretation here. What's this 1667 represent?
Y-axis.
But what did that mean in this problem here?
Median age.
Does that make sense? You can't have a median age of 0. Nobody's going to own a car at 0 years old, right? So while it is correct to say that should be on the y-axis at 1,667, having a median age of 0 is unrealistic. It's not real in terms of the problem setting. So while it is a correct sentence, that's on our y-axis, it's not a helpful sentence in this case because that's not a useful interpretive piece of data here. Okay. I can actually calculate these numbers M and B once I have the data. I showed you how to calculate R, and that was just a thrilling calculation, wasn't it? Same thing is true for M and B. I can calculate them. And I have a predicted Y value, and I can then go through and I can say, oh, well, I want the line that has the most small error. Okay, wait a second. Wait a second. Let me grab that picture again. Where did I put the picture? Here's the picture for our DMV data. Need a ruler. I want you to draw a line that you think is closest to all of these points. If I were to say, I'm going to go through these 2 points, I'd be fairly far away on those, wouldn't I? If I said I'm going to go through these 2 points, clearly I'm off a little on some of the others, right? Maybe I should kind of wiggle it in between all the points. Yes? Okay. There's a vertical gap between the edge of the ruler and each dot. That's an error between my predicted value for y and the actual value for y. The same thing is true down here. There's more data up here. Oh, there's still more, so I think I should move up, but yeah, so how do I draw this line? I want to find the smallest error. Finding the smallest of something is a calculus problem. Guess what we don't do in this class? Calculus. So there is a direct computation for M and for B that I'm not going to do. I'm going to let the computer do it. Boop. Here is the plot we came up with for our DMV versus wait time setting. Yes? You did this in chapter 3. I want a trend line. That's what we called it in Excel. I'm going to right click on one of these dots, and one of the options down here says add trend line. Boop. There's my trend line. Notice over here, there are all these options. And the only thing I've touched is linear, and they just named it automatic. So I don't have to worry about any of that. But over here at the bottom, there are some check boxes. And the bottom two say display equation on chart and display R squared. Not R, but R squared on chart. We came up with an R value for this. It's right up there, negative 0.0733. If I click on the trend line options that I want, it puts the information on the chart. Take the square root of 0.5369. Grab your calculator. Use your phone. What's square root of 0.5369? We'll make it bigger, bigger, bigger. Better? Square root of 0.5369 is?
Yes, it known the square root of 1.5.
Yeah, what's the square root of that?
So,
Which is the number we got for R, isn't it? Only they gave you the positive one because when you square a negative, it becomes positive as well. So this is the correct value of R squared. There's a reason they give me R squared instead of R. I'll talk about that more in a little while. But there's my equation. Negative 18.5x plus 458. What do those numbers represent?
The plus 458 is B.
Hang on a second. Yes, the 458 is B. But in terms of our setting, how would I interpret that?
the like
It's the intercept point on the y-axis. If I took this line and I kept going back, and kept going further and further to the left,
yeah.
I'd hit here at 458. but that's a geometric interpretation. What does it mean in terms of the problem setting of being at the DMV and windows and wait times and things like that?
That at 4:58, it's not significant anymore because you hit 0. Just like you were saying, at 0 years old, nobody's owning a car.
Significant is a word I want to stay away from unless I'm using p-values and alphas and testing things. I wasn't testing anything here, so I don't use the word significant. But that 458 goes with what number of windows? Does that make sense? If none of the windows are open, you're there forever, aren't you? So it's a useless number to us because it doesn't represent a real situation. In that case, I could say it doesn't mean anything, but I don't want to use the word significant. So yes, 458 goes with no windows being open. That would be where we cross the y-axis in our graph, but that's not a realistic thing. So what about the negative 18.5?
This is like the growth rate as the number of windows open increases. So
Keep talking. As the number of windows open increases, this is our growth rate.
wait time goes down
By
by negative 18.
goes down by 18.5.
Multiplied by windows.
Right. For every additional window we open, I'll lose 18 seconds of wait time. There's a quantitative relationship that I did not have with my ANOVAs. I said there was a relationship, but now I tell you how much. If we went from 8 windows open to 9 windows open, I expect that I could plug in a 9 there, and you could tell me what the approximate wait time should be. If there are 10 windows open, you put that in. If there are only 3 windows open, you can put that in. You can now predict, a predictive behavior. You can say, well, how many people are scheduled to work tomorrow? Oh, 7 people are scheduled to work tomorrow. I should expect a wait time of whatever that number is right there on the line, not what the actual dot is. Using my line to make predictions. The difference between the height of the line and the height of the dot, that's called a residual. So the difference here is the residual. You'll notice this residual over here on the left, that's almost 0. It might actually be 0. I don't know. But I can actually go through and get a residual for each one. And I want the smallest total residuals. Now, I don't care whether the residual is positive or negative. When we square things, negative things become positive. Big things become even bigger and small things become even smaller. So if I want to really look at my residuals properly, I should look at them by squaring them. And that's why this line is also called a least squares regression. Fit, how well this line fits, doesn't matter whether that slope is positive or negative. That just tells me which direction we're going, whether our relationship is positive or negative. The intercept only matters if the situation makes sense when this bottom independent predictor variable is 0. And in this case, it doesn't. In general, this is not cause and effect. I open another window, I expect wait times to go down. But there may be some brand new driver who's never filled out this paperwork before, standing in front of you, who's going to take 3 hours to do all the paperwork. Or you could be standing there and the computers could go down, and then you're just going to be there for a week. This happened to me on Friday. I went to the auto shop and I said, I'm here for my inspection. And they said, we're having a communications problem between the emissions machines and the computers in Harrisburg because the state controls all this stuff. And their office is closed today because it's the Friday after Thanksgiving. So I waited for 4 hours. it can happen. I'll talk more about the mathy bit and how we proceed with this, but we will not do these calculations by hand. Questions?
We're obviously not gonna have Excel during the test, so are you gonna show us how to do it on our calculators as well?
Absolutely, but I will also say that I'm not going to make you do this on the exam. I'm going to make you interpret it, which is why I spent all this time talking about what those numbers mean rather than how I got them. I can show you the math, it's gross, but no, you won't have to do it. I will see you all on Wednesday. You are reminded that our Chapter 11 homework is due then.